And I'm really excited to talk to you today about the world of world models. This is something that I have just been absolutely immersing myself in for the past really 2 years, learning more and more about it, getting really, really up to date in terms of all the different ways that it's applying to the field that I love so much, computer vision, and how it's really reshaping now other parts of the AI ecosystem, all from this one general idea. Now, we're going to have a lot of really interesting talks today about physical AI and some BLAs and things like that coming on. So I'm going to try not to stay too much in the technical details. I'm glad that I'm going first because I can give a really nice high overview of not only why we're shifting more towards this kind of world model world, but also kind of the kind of inspirations, why it's happening, what's shaping up, who's leading the field, and kind of how you can get started today. So with that being said, uh, where's a better place to start than why the hell are we doing this in the first place, right? What is a world model? What is physical AI? How did we get here? So thankfully, I don't have to make the graphic. My good friend Jensen, of course, has made a great graphic for me about why we're at this landscape of physical AI. What is this new word and why are we talking about it? Well, let's go all the way back. Obviously here we're starting with AlexNet, but it's really computer vision, where back in the day, the problem was cat dog, right? You have an image, is this a cat or is this a dog? And the machine learning model, its goal is to predict cat and dog. Now, importantly, let's keep in mind what we were doing before this, right? We were detecting edges, we were doing photogrammetry, we were doing many different ways to derive statistics from an image, for instance, to then make a prediction algorithmically if it's a cat or a dog, right? And maybe if you're from that era, you can think of things like SVMs and things like that as well back then. But it was cat dog problem, and we used convolutional networks. Slowly, we got better. We expanded this perception outside of just images. We can do audio, and eventually we can do other things like medical imaging. Then 2022 happens, 2021, ChatGPT comes out. It's a huge deal. I mean, AI is never the same. We figure out, hey, with the transformer, I can just keep throwing more and more and more and more weights at you, more data, more information, and you're just going to keep learning. And that's where we get generative AI. Of course, we have the ChatGPT stuff, but we also have image creation and synthetic data creation and new ways of generating things that we previously didn't have. We moved further along to agentic AI with coding assistants and all the other things that we have here. But keeping this in the realm of computer vision in the world that I live in, a lot of this was kind of moving into an area where, hey, before we were taking perception models, kind of those convolutional networks, and then eventually transformers of the past, and getting these insights, right? It was not cat dog, it was pothole or this is the box I'm supposed to pick up if I'm a robot. And then I could take those insights that I'm getting with perception models, pass it into some kind of algorithm that's controlling my robot, whether that's, a reinforcement learning network, or if that's really just pure algorithmic, pick up, move kind of problem. But now with physical AI, we're seeing this to become much more all-encompassing, right? In two specific directions. One, it's no longer just based on that pure media input of cat dog, right? We were thinking about images. We're not just looking at images now, right? We're looking at images, but I'm also interested in the velocity of the car, the acceleration of the car, the pose of the robot, the temperature of the motors. I'm interested in all the different actors around me. I'm interested in the material density of the object I'm picking up, right? All these new inputs that we previously just never really considered, at least all in one model, right? So it's much, much more than just whatever sensor input you're getting. It's how you're experiencing and feeling and interacting with the world around you. On top of that, we're no longer thinking about it in a problem state always where learn something, perceive something, and then pass that along, right? We want our models to be as kind of connected as possible and learning the task with as few kind of necessarily individual parts. I'll go into that to a little bit later, but we want it to be fully encompassing. We want our model to understand that the car is driving at 30 miles per hour, that the robot is walking down the warehouse, and that it needs to make specific decisions because of this, right? And that's how we've gotten to physical AI. It's now we're taking in the entire physical state of what is around us, and we're making actions based on that, right? We're no longer just perceiving a single media or perceiving certain inputs. We're trying to get as many inputs that represent that world around us and then take actions because of that. Well, then that leads us to a world model. What is a world model, right? We've been talking about physical AI, but where does a world model fit into physical AI? Well, the world model is a learned, unified representation of, well, of course, the world, right? But how does this differ from previous models, right? We're thinking about it where the world model needs to know geometry. It really needs to be really good at 3D structures. We need to know all the 3D representations. It needs to be really good at photogrammetry, videogrammetry, being able to understand how far away things are, and what are the shape of things, and are there gaps in things? If I poured a cup of water in it, would it spill the water, right? These kind of questions are obviously a little bit basic, but they inspire and drive all the different things around it. Including that, it's dynamics, right? Is this person walking across the street or are they standing on the corner? If I drop this box, is it going to fall and shatter, right? Like all these kind of things that are, when you think about bouncing a ball, how do I make a model how I bounce a ball and it comes back up to my hand, right? We have to understand how these things are going to interact in the environment around it. And then very importantly, semantics, or even more importantly, it's like behaviors of semantics, right? It's not enough to know red car anymore, right? Which is kind of where we were past 2 years or so with like clip models and things like that. It's not just red car, it's red car that's cutting me off, right? It's this blue car that it has road rage, right? It's this factory worker that is clearly upset, right? We need to know the behaviors of things because behaviors drive our actions that don't always necessarily need to follow the rules, right? And this is where we get to that last area, which is agents and intent. Who does what and why, right? Very classically, right? If you're teaching a car how to drive, I'm going to teach it how to drive in the lane lines. If a car is driving at me from the other side of the road on the wrong side and is going to hit me, well, I need to make sure my agent is well reasoned based on the geometry, the dynamics, and the semantics to know, hey, I need to also move out of the way into the other side of this lane, which might be an illegal action, to make sure that I then save or play, the safest option here, right? So it's much, much more than just following the rules, right? We need to understand the world in order to make the best decision. Really, how you can summarize this in a lot less words is we're learning states, not tasks or rules, right? We understand what is the state of the world around me, or what is the state of this data set or scene that I'm looking at, and then what is the objective afterwards, right? The end goal here is not to teach a world model how to do something, right? I'm not trying to teach the world model how to bounce the ball. I'm not trying to teach a world model how to drive the car, right? That's not really kind of what we're chasing here. The idea is that the model should understand how the world works, right? And being able to model the world. It needs to know if I bounce that ball, how high is it going to bounce up? It needs to know that if I drive through this puddle, how is it going to splash? Or how is this pothole going to affect me? Do I dodge the pothole or do I drive through it because it's the safest action, right? If we can learn the state of the world around us and not teach it for a specific task, then it's really going to open up the world of possibilities. So before we dive even deeper into here about why we're getting into this world model world, why we're kind of abandoning some of the things of the past, just a quick word about, who I'm from, Voxel 51, and my background. Well, if Jimmy didn't already give a nice tee off, we're from Voxel 51. We're the lead maintainers of the open source tool 51. If you don't know what a voxel is to a video, what a pixel is to an image. It's that volume element inside of a video. And if you don't know what the 51 is for, feel free to fire off in the chat. There's two main stories here that you can subscribe to. We have a, very nerdy PhD, loves, by the book co-founder. We have another PhD that's a little bit more loosey-goosey. They have different answers for this question. The nerdy one will tell you that, well, all the great technology of the future is going to be built in Area 51 like stuff, right? So we should be Voxel 51. The other co-founder will tell you that he just had 50 bad ideas and then he had 51. So you can pick, choose your own adventure, whatever you want. My name's Dan Goral. I'm head of technical partnerships here at Voxel 51, as well as a developer evangelist. My background is in all things physical AI before they called it physical AI. So I've been working with drones and cars and robots and small edge devices for the past 8, 9 years at this point. My main background now is typically in autonomous vehicles, so I apologize if some of my slides here are a little bit overshadowed there, but a lot of it too is just the autonomous vehicle space. It's much more mature than the robotics, but pretty much everything that I'm going to talk about here today, if I don't specifically call out robotics or AV, they kind of apply for both, right? So we're just going to keep on moving forward. So why is the current way not working? And I want to put an asterisk here that everything here is working with an asterisk, right? It's not that it's not working or it isn't working, right? It's just it can be better, right? And why are we moving to world models to be better compared to what we've been doing so far? Well, the number one thing that you need to understand is that there's so many steps to get a robot or an autonomous vehicle on the road and driving, right? And there's so many teams typically that go into doing this. And it's teams and teams and teams of people throwing one thing over the wall to the next, right? So we're thinking about perception, and then we're tracking different objects in the scene. Then we're predicting where these objects in the scene are going to go or what I should be doing. And then based on that, I'm going to plan what I should be doing. And then once I know what I should be doing and I know what's going to happen, and I think I know what's going to do, I then control the robot physically to then move around and interact with the scene around it. The issue with this is that there's just so much handoffs, right? It's so many different teams. Each model is typically specific for its own task, right? So we have this task and this task and this task and this task. And what happens is, like pretty much every machine learning model, and specifically in physical AI, we're going to have these kind of outlier use cases, right? We're going to have these things where the model fails in certain areas, and we want to make it better. But when you have so many different points of interaction, it becomes insanely difficult in order to pinpoint exactly where the issue is. Was it in perception? Could it be a little bit better? Was our prediction not as good? Was our planning not as good? And then when it comes to then replace one of these, right? Say, let's say a new tracking model comes out that we're really interested in. Do I have to redo my entire data pipeline? Like how agnostic is my data pipeline to take new models in and out in order to do this? And it just becomes a very hard problem to scale. That if you don't have this elite team with elite talent that's highly connected, it becomes very hard to do a full stack development of this. You're going to run into issues where new models come out and you're not able to grab it, or you're not able to get the right data. You're creating synthetic data, but when you create synthetic data, it's not what your ML team wants, or it's not what the data team thought it was going to be. And it just becomes a big game of telephone, both for the actual autonomous vehicle or robot that you're building, as well as the team that is developing it. I have this old slide that I thought I'd pull into this talk because I think it's really relevant for what we're talking about here. Now, this slide is from 2022. It's old. It's talking about synthetic data sets at that time. And synthetic data sets at that time were done in like GTA and Unreal Engine and video game engines, Arma 3 and things like that in order to generate these data sets for drones and robotics and cars and things like that, right? And some of this is still done today, but the point that I wanted to make in this slide was, look, like, this survey on the right here was at the time the state-of-the-art way of how to create a synthetic data set. And you can see that each one of these blocks typically is like representing a team, or like at least the stages here are representing teams at a company. And I was like, look, we have 17 different steps. Like if I just wanted to get a piece of data, like my car doesn't drive well in the rain, can you generate me a rainy scene? There's 17 steps to get there. I mean, that's insane. There's so many steps. There's so many areas where we can fail. There's this high barrier of entry to even understand what we're doing here. And this problem still rings true today. It's not about just synthetic data, as we'll take a look at it later, but this can be represented for anything within the physical AI stack. You're telling me that there's 30 different steps to get the robot to pick up the box, or that there's 30 different steps to teach my car that it can't make like an illegal U-turn. This is way too difficult, right? We need to try to make this a better optimized path where at least some of this is reducing the points of failure. The other thing that I've realized is one of the big differences about why we're shifting towards physical AI, world models, and things like that is what makes a good data set has changed, right? Specifically in physical AI and computer vision. To clear some of these misconceptions, we typically used to think that more data was better data, but that's not the case anymore. If this was the case, then we would have self-driving cars in every city in America today, but we don't, right? The issue is we don't have all the data that exists today, right? Even if you're Waymo and you have every single corner of San Francisco mapped out, right? That doesn't mean you have it in New York City and people drive differently in New York City. The pedestrians walk differently in New York City. The weather's different in New York City. And for that reason, we don't have Waymos in New York City, right? So it's not a matter of just getting more and more data and the car will drive, right? We need to be able to find all these specific edge cases and scenarios and be able to model all of these to make sure that the car drives safe everywhere, not just in one area. And the same thing goes doubly true in robotics, where there's just not enough data. And it's not so simple that I can just go drive the robot around and find all these edge cases. The other issue is that we don't know sensor placement yet, right? This is an unsolved problem, right? If you want the biggest example and paradigm here, it's going to be the fact that Waymos have like 23 different sensors on them and Teslas don't use LiDAR. But both seem to be self-driving today without much problem. So if Tesla's all the way here on one end of the spectrum and Waymo's all the way over here on one end of the spectrum, then who's to say who's right? We don't know the answer here. What we know does work, however, is usability is really important, right? We want to make sure that if we're spending all this time collecting data and generating data, we want to make sure that we can actually use that data, right? In order to do that, we need to confirm that all the physical to digital translations are as accurate as possible, right? It's not just looking at a cat and a dog image, right? It's the velocity, it's the poses, it's the sensor modalities working together for multimodal applications. And all this is very complex to manage, but we need to make sure that when they're working together, we're painting the best picture for our model. On top of that, because of this, synthetic data is just becoming essential. Like, it's not an option anymore, right? It's not, should we use it? It's just how much we should use it, right? I think some of the numbers that popular companies like Wave will throw out is that for every one real scene they're training on, they have 20 synthetic scenes that are just different alterations of that scene. And so it's just way better that whenever you find this scene that's actually interesting for you, that your car or your robot was struggling on, well, let's go generate 100 different versions of that scene to make sure it won't struggle on it in the future. So it's just not becoming an option. You have to be synthetic data. And as much metadata as you can pour in, that physical context, the motor speed, the velocity, the acceleration, the poses, throw all of that at your model to see how much of that state it can take in. And then the model will tell you what's important and what's not important, right? But we want to build that state for the models that we're building today. So with all that being said, now that we're a little bit prefaced on what we think the leading kind of models are and what do you think the largest blocker is for physical AI? I'm going to pause here for 30 seconds and take a sip of my coffee. I want everyone to think, what do you think the largest blocker for physical AI is? Just guess, put it into the chat, see what other people's thoughts are. I'm really curious to see what you guys think. There's a couple good directions you can go in. Well, spoiler alert, it's not going to be any of these three, because if it was any of these three, then you wouldn't really be blocked. We have companies that have these three. So powerful GPUs, if you're a big company, you're going to have powerful GPUs, right? Even the smaller companies are going to have some amount of GPUs, but it's not a problem where we can just throw 100 million GPUs at it and all of a sudden you have self-driving cars, right? If that was the case, we would have self-driving cars. It's not balanced amounts of data. All these companies have balanced amounts of data. Trust me, I've talked to a lot of the leading AV companies in the world. I probably have chatted with at least 60 to 70% of the AV self-driving teams in the world today. They all have balanced amounts of data. This is not a problem, right? And it's still not helping them drive their cars or do their robots or anything like that. And it's not top tier talent. Of course, these incredible talented engineers are tough to find. Of course, they exist out there. But I've seen very talented engineers still struggle. I've seen really talented teams not be able to overcome certain gaps, right? So it's not any of these three. So that being said, if it's not any of those three, what is the actual problem here? The actual largest blocker for physical AI today is just time. It's just time. And what I mean by that is, let's say you have a car or a robot. I'll do a robot example this time. Let's say we have a robot and the robot works really poor in the snow. It just doesn't work that well in the snow. It cools the motors down, the calibration falls apart, and it doesn't move the same way, and it causes it to fall over and such. It wasn't represented well enough in its training set, or in the specific scenario, it doesn't do well. Am I supposed to go wait until the next time it snows to go get my snowy data? Of course not. right? Similarly, how do I know that even if it did snow, that it was going to be correct? Like that it was the same type of snow or it was the same temperature? Was it the temperature? Was it the snow? We don't have time to figure these things out, right? And I don't have time to go do all this in real life. I can't go do all this in real life. That's the most important part. I can't go get the data in real life. So if that's the case, and this is the largest blocker for physical AI, it's not about how many GPUs I have. It's not about the amount of data it is. It's, am I training my GPUs the right way to save time efficiently? And am I taking the most amount of training runs efficiently so I can train faster in the given amount of time I have? And is it, that I'm picking the right data through curation methods in order to save time on not training on junk, right? I'm only training on the things that matter. So if we have this, how do we solve this problem? I'll give you an example. Got this example from Wave. It's a great example. We call this a zebra cross in self-driving. I have this woman who's crossing with her baby. We have a bicycle that's going down the street. And I have this man that he came a little late. The car still needs to stop. Now, zebra crosses are infamous in self-driving for being very difficult. They're not like a typical intersection and such. So maybe I wanted to find more zebra crosses, right? I wanted to go generate. I'm not going to go drive around and find every zebra cross. What if this person decided not to walk? What if the bicycle cut me off? What if there was another car coming in, right? All these questions about how I can make a zebra cross more difficult. Well, I'm not going to go wait at a zebra cross to figure all these out. If we can't control time, we just need to control the world, right? And that's where world models are coming in. That if all these videos we're looking at here right now are just digital twins, synthetically created versions of the same model, where I can now go into this and move things around and generate novel views and drop in the pedestrians and drop in the cyclists and do all these things. Well, that's actually what's actually interesting for us, right? That is what we need to do, that we can take these hard scenes that we found and curated and then move them through the world models to then generate all this data to close our gaps. I'm going to stop right here before we jump into kind of the current state. Hopefully everyone's up to date on why we're doing world models. Doesn't look like we have anything in the Q&A today, so I'm going to keep right now. I'm going to keep moving on, but if you have any questions, drop those in.
So I'll jump in here
So
real quick, Dan. Someone made the comment that simulation and environments are still not very good. I'm assuming this is something that you will cover.
absolutely, I'm glad you're leading me right to where I'm going. So this is great. So I'm really happy about it. But we're going to get to that at the end. So let's look at some of the world models in practice today. The first and foremost thing is that world models are not a solved problem today, of course. Sometimes we get hallucinations, like we'll see in some of these examples here, where my scene just really begins to break down. And as we see in some of my Gaussian splatted scenes here, you're going to get noise, your labels might start to disappear, you might get what we call ghosting. It's tough. It's a tough problem. And, it's still very new for all of us. However, here at Voxel 51, we're building what we're calling the Physical AI Workbench to help solve this problem. Uh, with bad data, we might have issues, but when you pass an audit is what we're calling, you're going to get those great reconstructions. This allows you to get these bad cases here, find the issues, and then correct them to make sure you're getting clean data sets. And these are all from open source examples here, right? So on the top, we have a new scenes, in the middle is Waymo, and on our bottom is PandaSet here. The whole goal of the Physical AI Workbench is to help get your data production ready. This is no more expensive training runs that fail, no more model input mismatches. All that complex state mapping that we were talking before is a very difficult problem. But there are ways for us to confirm that the state is as best being communicated to the world model or that you're using, or the Gaussian splatting method that you're using, in order to get the best representation of your model or your data set. This also allows you to democratize your data. We talked about the problem that everything is siloed and that everything is getting thrown from one team to another. But with Voxel 51, you can share this across your entire organization, creating these rich data pipelines for your whole organization to use and instantly transfer to any team for any convention. We get rid of that problem where everything is in a specific format or specific standard. We only accept new scenes, or we only do the robot, or we only do whatever it might be for your use case. Once you're in the Physical AI Workbench, everything is completely agnostic, right? We're mapping the state. We're showing you the state. And if you're missing gaps in your data set, we can help fill in that state with photogrammetry, videogrammetry, and other ML models to help build an even better state for you. Overall, this is how the diagram looks like. You ingest your data inside of Voxel 51. We'll perform that audit on your state. We're going to check all the metadata that you stored on it. We're going to check all your timestamps for outliers, jitter, monotosity. We'll check all the calibrations inside of your data set for your poses, intrinsics, making sure everything is aligned as best it possibly can be. And then we're going to check the LiDAR camera collaboration, that projection, to understand that all the different multimodal experiences that you might have on your data set are working in unison. Everything is synced well, everything is calibrated well to understand that whatever you're going to pass that into your next world model training, or if you're going to take advantage of tools like Omniverse or Cosmos, which we're going to talk about in a little bit here as well, that you're getting the best state possible for those models. Now, of course, not all of this is going to be available. People make mistakes. There's errors in data sets, and we need to clean things up. So if we find something in the audit that is broken and not working, we actually automatically can help fix it for you by enriching it. This is by using classical photogrammetry, some of the best techniques coming out of old school shops like Pixar and video game technology, where we've been using this for years and years and years. We don't need to abandon it just because we have a new problem. We want to make sure that we're taking the best from both fields, both AI and classical 3D geometry networks and teams, to make sure that we're filling in and giving the best representation of our data set. This actually leads to the point where your data set that comes off your rig, whether it's a robot or a car or whatever vehicle you're working with, a drone, is actually better when it's represented to the world models or VLAs that you're training, to make it even better experience for everything, and help it learn exactly what is happening in the scene than it would if you just trained on that raw data alone. All this is built inside 51 Enterprise, so you can load directly into a cloud deployment, have a unified view of all your data. Everything is queryable. If you want to find those rainy scenes, if you want to find those cut-ins, if you want to find that road rage scenario, we can help find that using queries, semantic text, as well as anything attribute you store on top of your data set. Everything will be immediately data integrity checked on ingest, and everything is a shareable, reproducible workspace. So you can run experiments, share with your coworkers, and evaluate together. Now, hopefully Jimmy dropped a link to the Physical AI Workbench. I don't know if I'll have enough time to give a full demo of everything that is capable of, but I'm sure we have a link where there's the webinar, the webpage, and much more if you're interested in trying it out, getting those really high scale reconstructions or getting your model ready or data set ready for that world model training. I highly suggest you take a look. We'll also be open sourcing some stuff in the near future to kind of get a little bit more into the hands of the community. However, I'm glad we had the question earlier. What's next for world models? Well, there is a huge schism on the horizon, and it's so exciting for me, right? I haven't been this excited about a problem since, hearing Tesla and Waymo and Wave go back and forth about what's the best way. This is probably the most exciting thing I can think of for physical AI. That's just so, I can't understate how excited I am for it. So what is it? We talked about world models so far. They're getting much better. That's all you really need to know. No surprise here. AI, it's getting better. Who would have thought, right? We have some open source options. Cosmos is probably the best open source environment out there today. We have some open source research, I guess you could call, where Wave is always really, really great about talking about their world models. Gaia 3 is their latest one. There's a paper. You can go and read it. I actually remember sitting in 2023, I think it was ECCV or ICCV. I was in a Wave workshop. There was 30 people there. That was the first world model that I've ever saw. They talked about Gaia 1 at that time and how it helped them and how they were using so much of it in training. And I'm positive I talked to them. They won't talk about it publicly, but Tesla and Waymo have the same thing and they just keep it secret, right? They have their own world models. Everyone that is very serious in physical AI is using world models today. However, there's something much bigger that's happening slowly and quietly right now. Today, we're using world models predominantly to generate synthetic data, right? It's taking that scene and making it a rainy day, a snowy day. What if the car turned left? What if the car cut me off? What if the robot dropped the box? What if someone bumped into my robot? All these type of things. You generate the synthetic data. It usually comes out as a USDZ or USD if you're familiar with that. It's the Pixar format. It could be a PLY, Gaussian splat, video, you name it. Doesn't matter. We're creating synthetic data with world models today. And then you plug this into Carla, Isaac Sim, and other extremely popular simulation tools. But why would we stop at creating data? Obviously, you can go and create like VLAs and world models and stuff like that. That's not what I'm talking about here, right? Why would we stop at creating data for world models? There's no good reason. And that's why Alpasim is a huge deal. This is a simulation platform that was announced at CES from NVIDIA. It's the first of its kind. It only released less than a month ago. It's very new. So this is very hot off the press. And it's challenging traditional sim paths. And it says, look, I understand you want to use Unreal Engine or Unity and these kind of traditional sim paths through Carla or Isaac Sim, Isaac Lab. It's all very physics accurate. It's very well practiced. There's whole teams dedicated to these simulation environments. But when you think about when you're training a physical AI model, what is your goal? And I'll do a car example because the car example is the most easiest one to picture. If I'm training a car, why would I care what happens after I hit the tree, right? If I'm training a car, why am I doing it in a video game engine? So I can see it drive, so I can drive it myself. If am I doing a simulation environment? Am I moving the actors around? Should I be responsible for saying, oh, instead of turning right, this car should turn left? Or instead of this car cutting me off to the left, it, veers to the right. Why am I doing this by myself? Why is this a manual process? Why do I have to pass my data to two, three, four different teams in order to get to the best simulation environment? Once again, what is my goal? What is my goal for building a self-driving car? My goal is to build a car that doesn't crash. Stop. That's it. That's my goal. And so after it crashes, I don't care what happens anymore. I don't care if it hits the tree and the tree falls over. I don't care that if it hits the curb and flies off or whatever. I don't care. It hit the curb. It's not supposed to do that. So at that point, it's instantly a failure. I shouldn't have hit the tree. I shouldn't have hit the curb. I don't need to see the fact that it hit the curb, nor do I need to be the one telling my model to, generate traffic. Like, I'm very interested in intersections where I make a U-turn. My model should know that it doesn't have enough U-turns and just generate that for me. And that's exactly what Alpasim is doing. It's allowing you to use world models to simulate as well. And it's such an innovative idea. And like, look, it's very early days. There's a lot of pros and cons. I can give you like the easiest con if I want to be devil's advocate, right? The only thing that this is really bad at right now is if I'm training a car or a robot and I'm supposed to be driving in like mud or snow, I'm not going to be able to use a world model to simulate slipping on mud and snow today. It's just not going to work, right? We're going to have to stick to the traditional engines there. But even in those engines, that's an insanely hard problem. And it's not going to be that long until a world model can just generate and simulate slipping in mud or moving slower in snow or slipping on ice. And so I just want everyone to take one thing home, right? When we're thinking about physical AI, what is your goal, right? And why, what are the tasks that are still human in the loop today that have nothing to do with, safety quality and things like sure you can define certain scenes, but Alpasim is just so exciting because now it allows you to just go way faster. I don't have to have a simulation team. I don't have to integrate into Carl. I don't have to do all these manual scene generations. Alpasim will generate the traffic for me. It will simulate the traffic for me. I don't have nearly as much overhead. It's way more performant than traditional sim engines like Unreal and things like that. And it just takes so much of the load off of what is stopping people today. And with Alpasim, it's just such an exciting opportunity to really drive forward the field of physical AI and how we think about world models, where if we're really trying to train world models to represent the state of the world and training the world today, then why wouldn't that also be simulated in just another world model, right? Why wouldn't we train these models to continuously try to make themselves better to build the best self-driving car? It's so exciting. I think it's really going to be a big deal. look, simulation is not going anywhere. Carla, Isaac Sim, Isaac Labs aren't going anywhere. They still have a very big use case today. This is not something that's gonna be completely negligent in like 6 months or so, but it is just so exciting about what the future lies in this type of space. So if you're interested, this is something that we're actually building in the Physical AI Workbench today. It's going to be in our next release, our first integration with Alpasim. Fortunately, the input to Alpasim is NUREC in USDZs, so it's very easy for us to plug it in. I'm happy to talk more about it offline, or if you have any other questions about physical AI, I'm going to drop my LinkedIn here as I go through my Q&As here. But thank you for your time. This is a topic I'm super passionate about, and I'm always happy to share and kind of bring it to the field, all the latest stuff. And I appreciate your guys' time for sticking around and listening. So I'm going to take some time to look through some of the Q&As here.